In theoretical physics, an action is more than a formula. It is the master instruction that tells a system how to behave, the blueprint that determines how reality organizes itself. From the curvature of spacetime, to the vibration of strings, to the entropic architecture beneath the universe itself, actions define the rules of existence. Today, we explore four of the most important actions in modern physics: the Einstein-Hilbert action, the Nambu-Goto action, the Polyakov action, and the General Obidi Action of the theory of entropicity. Let's begin. The Einstein-Hilbert action is the foundation of general relativity, the theory that describes gravity not as a force, but as the curvature of spacetime itself. Its ingredients are simple but profound. The spacetime metric, which tells us how distances and times are measured. The Ricci curvature, which measures how spacetime bends. The volume element, which tells us how to integrate over curved geometry. Newton's constant, which sets the strength of gravity. And the cosmological constant, which controls the expansion of the universe. When you vary this action with respect to the metric, you obtain Einstein's field equations, the equations that describe black holes, gravitational waves, the bending of light, and the evolution of the cosmos. This action is elegant because it compresses the entire behavior of spacetime into a single integral. It is the action of the macroscopic universe, the world of galaxies, stars, and cosmic structure. Now we zoom down from the cosmic scale to the microscopic scale, to the world of strings. The Nambu-Goto action describes a relativistic string by the area of the surface it sweeps out as it moves through spacetime. This surface is called the worldsheet. Imagine dragging a rope through water. The rope traces out a surface behind it. The Nambu-Goto action says, a string evolves by choosing the worldsheet with the smallest possible area. This is the string theory analog of a soap film, minimizing its surface tension. It is a beautiful geometric principle, simple, intuitive, and deeply physical. But there is a catch. The square root structure in the action makes it extremely difficult to quantize. This is why the Nambu-Goto action is perfect for classical string dynamics, but not ideal for quantum calculations. To solve the quantization problem, Alexander Polyakov introduced a revolutionary idea. Instead of letting the worldsheet geometry be determined entirely by the string's motion, he introduced a new, independent metric on the worldsheet. This transforms the action from a square root form into a quadratic form. This change seems small, but it unlocks enormous power. The action becomes easier to quantize. It becomes conformally invariant, meaning it respects angle-preserving transformations. It becomes compatible with two-dimensional quantum field theory, which is the mathematical heart of string theory. The Polyakov action is a foundation of quantum string theory. It is the version used in textbooks, research papers, and modern formulations of string dynamics. Now we move beyond spacetime itself, into the deeper informational substrate proposed by the theory of entropicity. In ToE, spacetime is not fundamental. It emerges from a more primitive structure, the entropic manifold, and the dynamics of this manifold are governed by the General Obidi Action. The Local Obidi Action, or LOA, is the entropic analog of the Einstein-Hilbert action. But instead of describing the curvature of spacetime, LOA describes the curvature of the entropic manifold, the deeper informational geometry beneath reality. Its ingredients include the entropic metric, which measures distinguishability rather than distance, the entropic curvature, which describes how distinguishability bends and flows, a field that encodes entropic density, including the lane-2 threshold, the smallest entropic difference that can produce a physically distinct state. LOA tells the entropic manifold how to curve. And when this entropic curvature is projected into the emergent sector, it becomes the curvature of spacetime. In other words, spacetime is the shadow of entropic geometry. The Structural Obidi Action, or SOA, is the entropic analog of the Polyakov action, but with a crucial twist. SOA contains two major components: a Polyakov-like kinetic term for entropic world volumes, surfaces or volumes embedded in the entropic manifold, a spectral sum over entropic eigenvalues, the frequencies or modes of distinguishability. This spectral term is where the magic happens. It encodes the lane-to distinguishability threshold, the no-rush spectral gap, and the entropic mode structure of the universe. In ToE, distinguishability is not continuous. It comes in discrete steps, and the smallest step is ln2. SOA captures this discreteness through its spectral structure. Let us summarize the differences clearly. Einstein-Hilbert action lives on spacetime, governs gravity, uses curvature of spacetime. Nambu-Goto action lives on string worldsheets, minimizes area hard to quantize. Polyakov action lives on worldsheets, with an independent metric, quadratic and quantizable. Foundation of quantum string theory, General Obidi Action LOA plus A, lives on the entropic manifold. LOA gives entropic curvature. SOA gives entropic spectral structure. Spacetime and strings emerge as projections of entropic geometry. Each action governs a different layer of reality. Einstein-Hilbert gives macroscopic gravity. Nambu-Goto gives classical strings. Polyakov gives quantum strings. LOA gives entropic geometry beneath spacetime. SOA gives spectral structure beneath quantum behavior. Together, they form a hierarchy. Entropic manifold gives spacetime, gives strings, gives fields. The General Obidi Action sits at the deepest level, the most fundamental layer of the theory of entropicity. From the curvature of spacetime, to the vibration of strings, to the entropic architecture beneath reality, actions are the mathematical engines of the universe. The General Obidi Action unifies them by revealing that spacetime and quantum behavior are shadows of a deeper entropic geometry. Thank you for watching, and welcome to the frontier of the theory of entropicity ToE.